quickly. We're going to go through these and talk a little bit about each one, hopefully. Okay, an arc with endpoints that are the endpoints of a diameter of a circle. So remember that an arc is just a part or a piece of a circle. So what part of a circle has the endpoints of a diameter? Semicircle. What's the measure of a semicircle? 180 degrees. An angle, number 2, an angle whose vertex is the center of the circle. We learned about 4 different types of angles in this class. And it all boils down to where is that vertex located. So when it is the center of the circle, we call that type of angle central angle. It kind of makes sense. If the vertex is the center, then we call it a central angle. Every single one of these angles that we've discussed has some sort of intercepted arc. What is the relationship between a central angle, its measure, and the measure of the intercepted arc? They are the same. They are equal. Those measures are equal. If you have a central angle, the vertex is the center of the circle. Number 3, the exact point that the circle and a tangent line have in common. What is that? Point of tangency. And if I were to draw a radius to that point of tangency, then what is the relationship between the radius and that tangent? Okay, and what do we call those two objects if it forms a right angle? Perpendicular. So if you draw a radius to a point of tangency, that exact point where a tangent and a circle have in common, you draw a radius to that, then those two objects, the radius and the tangent, will be perpendicular. We have a theorem about that and proved it in your notes. Last 2 classes. A line that intersects a circle at exactly one point. Tangent. Segment whose endpoints are on the circle. Chord. Part of a circle that lies in the interior of an angle. It's just 2 words. What is a part of a circle called? Arc. Okay? There's many types of arcs out there. This, I'm referring to the one that is in the interior of the angle. And I've said the term today multiple times. I asked you about what is the relationship between a central angle and this. This is what we're talking about. Intercepted arc. That is the arc that lies in the interior of an angle. You have to be able to identify the intercepted arc, because all those theorems that we talked about last class, about the angles, those are all referring to the intercepted arcs. There may be 1 intercepted arc, and there may be 2 intercepted arcs. Those are the arcs that are in the interior of that angle measurement, and it's on your notes twice, because it says on the 2nd page, in the description it says, notice that the major arc associated with points A and B lies on the outside of the angle, while the minor arc lies in the interior. That arc is said to be intercepted. And then again, I typed it out. An intercepted arc is the arc that lies in the interior of an angle. So it's very important you know. I put it twice in your notes. This one, a line that intersects a circle in 2 points. What is it? Secant. Okay, so the fact that I said it is a line, that means that it exists on the outside. That's the difference between a secant and a chord. A chord starts and ends on the circle, and it never goes beyond into the exterior of the circle. So a line clearly will go in both directions. It exists outside of the circle. Part of a circle that measures less than 180 degrees. Minor arc. Okay, so part of a circle that is an arc, but I have to be a little bit more specific and say that this is a minor if it's less than 180 degrees. A chord that contains the center of the circle. Diameter. And a segment whose endpoints are the center of the circle and a point on the circle. Radius. A radius. Wonderful. We're going to segue into our homework. Springboard page 352. Page 352. Now this first part is about central angles. This first homework page is about central angles. And just so we're all on the same page, what is the relationship between the central angle and its intercepted arc? What? Say it louder.
The measures are the same.
Measures are the same. Central angle and the intercepted arc, the measures are the same. So since they're telling us that the measure of this arc is 96, the measure of that angle, since it's a central angle, is also 96. Okay, questions on this page? 8 through 15, but not 12. Cool. Let's move on to the next one. 357, Springboard page 357. This section is all about inscribed angles. Inscribed angles, where the angle's vertex is on the circle somewhere. So in this diagram, there are 4 inscribed angles. You got angle A, angle B, angle C, and angle D. Now this is called an inscribed polygon. A little bit more specific, we've got an inscribed quadrilateral. Okay? There's a couple of theorems that we learned. First off, if you have an inscribed angle, the vertex is on the circle, then that angle is going to have an intercepted arc. This one is the intercepted arc from A to C. What's the relationship between the angle measurement, the measure of angle D, and the measure of the intercepted arc A, B, C? 1/2. It is 1/2. That's because it's inscribed angle. The vertex is on the circle. Who remembers what happens with, nope, not yet. Never mind. I want you to go ahead and pull out the notes. So look at your notes for me real quick. You should already have them out. Those are side by side. Unfortunately, last class we ran out of time and we didn't get a chance to talk about these 3 theorems at the very, very bottom of the third page of your notes. The third page of your notes. The first one. This is that diagram from your homework that I was just marking up. You have an inscribed quadrilateral, and that means that all 4 vertices of the quadrilateral are on the circle somewhere. And so these are all inscribed angles, all 4 of them. So what I would like for us to do is we're going to split the class. These 3 rows. I want you to focus on angle W and angle Z. And I want you to tell me what the intercepted arc for each is. You can just write it on your piece of paper. So I have angle W, and this is the intercepted arc. Angle Z, and this is the intercepted arc. These 3 rows. Same exact thing, but you're going to look at angle X and angle Y. You're going to focus on angle X and angle Y. I want you to tell me what the intercepted arc is for each of those angles. If you don't know what I'm talking about, this is what I mean. Here is an inscribed angle. Its intercepted arc is arc AB, because it lies on the interior of the angle. Please use 3 letters for every single one of the intercepted arcs. Just make things easier. Now that you've found the 2 intercepted arcs, I want you to tell me what is the sum of the 2 intercepted arcs. So look at your diagram and tell me, what would the sum of the 2 intercepted arcs be? Discuss with your row mates, the 2 sides of the room, discuss with each other. Check to make sure that you have the correct intercepted arc. This is the angle, this is the intercepted arc. Remember that we can switch the 2 letters, those can be switched. So the correct answer for the sum of the two arcs, doesn't matter which ones you're talking about, these two arcs will be 360 degrees. What I have here are these two arcs kind of outlined with squiggly lines. So it takes up the entire arc. So when I add up those two arcs, I get 360 degrees. But inscribed angles are creating those. What's the relationship between an inscribed angle and its intercepted arc? It's half. So if these two angles together are intercepting the entire circle, then what are these two angle measurements added up together then? 180 degrees. It'll always work out. Okay? So, theorem. If a quadrilateral is inscribed in a circle, then the opposite angles will always be supplementary. And those are the angles that I assigned you. So this half, you guys had W and Z, and we noticed that the intercepted arcs by both of them ended up to be the whole circle, which is 360 divided by 2, 180. And then this other side of the room, I gave you those two opposite angles. Same thing happened. Together they intercepted the whole circle. Divided by 2 gives you 180 degrees. Okay, for this guy, this angle here with the vertex of D and this angle here with vertex C, does everyone notice that they intersect the same arc? Okay, what kind of angles are these if we had to classify them? No, not acute, obtuse, right, or nothing like that. Using our new circular terms. How is it related to, is it a central angle? Okay, what's the other word that we learned? Inscribed angle. Okay, so the vertex is on the circle, then it's an inscribed angle. I know we've said this a million times today, but what is the relationship between the measure of the inscribed angle and the intercepted arc? 1/2. So if this intercepted arc was, I don't know, it really doesn't matter, 66 degrees, then what would the measure of angle D be? 33. What would the measure of angle C be? 33. So, in the end, if two inscribed angles intercept the same exact arc, they have to be congruent. They have to be. They have to have the same measurement. If two angles intercept the same arc, they have to have the same measure. And the very last thing is we need to know this theorem, then also the converse of it. Let's just look at the diagram and see what's happening. Is there anything special about segment AB? It's a chord. What about segment BC? It's also a chord. Anything special about AC? That is a diameter. Yes, it's a chord, but it's a special chord that clearly contains the diameter. So what could you say about arc AC? It's a semicircle. Okay? Because that's what creates semicircles, are diameters. Therefore, what is the measure of angle B? Its intercepted arc is here because, so what is the measure of angle B? 90 degrees. Okay? Making triangle ABC what type of triangle? A right triangle. So the theorem says that if a right triangle is inscribed in a circle, then the hypotenuse is a diameter, because that 90-degree angle is going to intercept a 180-degree arc every single time. So that means those two endpoints, if you connected them, it'd have to be a diameter, because diameters create semicircles. But there's also a converse to it, and this diagram is actually the converse of what is written here. So this says, if you have an inscribed triangle, and you know that one of your side lengths is a diameter, then you can conclude but it's a right triangle.